Welcome to this physics prep. Today we're going to be doing medical physics. So this is everything that you need to know for the 90th century 2 syllabus. For those who are writing, good luck. But this is going to give you a brief overview of everything that you need to know for the medical physics part. So the course outline. So in this tutorial, we're going to look at ultrasound, X-ray scanning, CT scanning, PET, positron emission tomography. So CT scanning is just under X-rays. And then we're going to do a walkthrough with 3 exam questions afterwards. So ultrasound. What is ultrasound? So basically ultrasound is just sound of frequency that is greater than 20,000 hertz. That is basically that all it is. Basically that all it is. We went to, so what is ultrasound? Is a better definition. It's not required by the syllabus. For those who want to gain a more insight, provide the definition. It is medical imaging technique that uses high frequencies waves to create images of the inside of the body. It is commonly used for various diagnostic purposes, i.e. to monitor the development of a fetus during pregnancy. So the key points about ultrasound, how it works. So an ultrasound machine emits sound waves that bounce off tissues and organs. The reflected waves are captured and then converted into images by the machine. The types of ultrasound that we'll look at for this syllabus is just 2D ultrasound mainly, and then 3D we won't really look at it. It produces flat surfaces of the structures being examined, and then 3D produces three-dimensional images. Key concepts of the production of ultrasound, we used what is called piezoelectric effect. In the next slide, we'll show you how exactly that works. So the piezoelectric effect. So what we have is we have certain materials. These materials are called known as piezoelectric materials. So when they are compressed, when pressure is imposed on these materials, an electric charge is built up, is formed, because when you compress them, you distort the ions that are in the crystal. So there's positive and negative ions. So when you compress these, you sort of distort the ions, and then the negative, you produce an electric field in between because the negative charges are displaced to one side and the positive to one side. Right? So this is the basic working principle of an ultrasound transducer. An ultrasound transducer contains one or more piezoelectric crystals. When an alternating current is applied to these crystals, they vibrate quickly, producing sound waves at frequencies higher than the audible range, which is typically above 20,000 hertz. Okay. So here is how it works. So we have this is called a sonogram device. This is the one that is used specifically for the medical diagnosis in radiology, especially for checking up on pregnant women. So you have your electrodes right here, the electrodes, and then you have your piezoelectric crystal in between. So what happens is the process can be summarized as follows. So you have an electrical signal. An electrical signal is sent to the piezoelectric crystal, right? And then, so what happens? What causes the vibration now is that the electric signal, it's an alternating PD, so it continuously changes at the frequency that we need our ultrasound to be. So if you want to make ultrasound that is of let's say 20,000 hertz, we're going to apply a frequency, an ultrasound, and we're going to use a crystal that is dimensions, which when they vibrate at a certain frequency, they'll produce the ultrasound that we need, right? Okay, so let me show you how that works. So basically in the crystal, you have your ions, and they are distributed well, and you have no net charge. You have no net charge. You have no net charge, right? So what happens is when you apply the PD, there's an expansion, a stress. Stress is applied, right? You apply stress to the crystal. So this causes, let's say this side is at one instant, this is negative polarity, and then this is a positive polarity from the alternating PD. Remember, these are the electrodes. These are electrodes, right? So what happens is at one point you have your positive charges aligned to one side and your negative ions to one side. So when you continue to change the polarity of the alternating PD, that will cause the crystal to vibrate as the ions rush back and forth from this side. As the ions, positive ions, when this is negative, the ions move to the negative side, and then when this is positive, the negative ions will move to the opposite side. So when that happens, you produce a vibration. That vibration produces ultrasound that we need. So this is for the production of ultrasound. For the detection, remember we said ultrasound is transmitted into the body and then it's reflected at the boundaries. When it's reflected back, how do we detect it? When the ultrasound is incident on the crystal once more, it causes a compression this time around, the opposite effect of the caused by the alternating PD. So this time the opposite effect happens, and then the ions are displaced in the opposite directions. This will give us a pulse. This now produces a pulse in the electrodes, and then this electric pulse is detected, amplified, and then displayed on the screen. Frequency control. So frequency of the ultrasound waves is determined by the characteristics of the piezoelectric material and the design of the transducer. Like what I was talking about, the dimensions of the piezoelectric crystal that we have, the dimensions will determine what frequency is going to be produced. So they are specifically cut to produce. So each electric crystal is cut to produce a certain frequency for ultrasound. Right? So high frequency are better cause for better resolution in imaging. The reception I explained in the earlier slide. The same transducer can also act as a receiver. When sound waves bounce off tissues and return to the transducer, they create vibrations in the piezoelectric crystal, which generates a corresponding electrical signal. This signal is then processed to form images or gather data. All right. So for the calculations now, as required by the syllabus, we're going to look at the specific acoustic impedance. It is defined as the measure of how much resistance an acoustic wave or an ultrasound wave encounters as it travels through a medium. This definition is not required by the syllabus, but we'll see an example of how the specific acoustic impedance can be applied. All right. Acoustic impedance it is mathematically defined as the product of the density of a medium and the speed of sound within that medium. Remember, the speed of sound varies if whether it's in air, it's in water, or it's in another solid material. It varies. So when it comes to the boundaries of our skin, right? Remember, ultrasound is used in medical diagnosis. The bone has its speed of sound in bone has its own value. Speed of sound in tissue has its own value. Speed of sound in blood has its own value, and all that, as you see later in the example that we'll do. Intensity reflection coefficient, right? So this one it's a measure of how much out the sound intensity, how much of the it's a measure of the ratio between the incident and the reflected intensity, right? It shows us how much of a wave is going to be reflected between two boundaries. So these two boundaries are the Z1 and Z2, which are the specific acoustic impedance for the first boundary and for a second boundary. So let's say between tissue and bone. So between those two, you have your specific acoustic impedance, which is the density multiplied by the speed of sound in that particular medium. And then so it is the difference divided by the summation of the two acoustic impedances, and then you square them. When you do that, you get your ratio between the incident and the reflected intensity. So as it is a ratio of the incident intensity and the reflected intensity. A high value, a high value of a high value of A shows that most of the beam is going to be reflected, right? It's it shows that most of the beam is going to be reflected off, and then a low value shows that transmission, most is transmitted through. Now, there's another concept, absorption of ultrasound. So when ultrasound is incident on a medium, there's a reduction in its intensity as it travels through, as the energy is absorbed by the medium, right? So for the Cambridge syllabus, we have a formula that we can calculate how much of the incident beam it will be left after it has traveled a certain distance in a certain medium. Right? So the formula is I is equals to I naught E to the power negative kx, where I is the intensity of the ultrasound after traveling a distance, and then I naught is the initial intensity of the ultrasound. With alpha is the linear absorption coefficient. This depends on each particular medium. It shows how much of the beam or the ultrasound will actually be absorbed by that particular medium. Let's say if it's bone, it will have its own linear absorption coefficient. If it's muscle, if it's tissue, if it's air, if it's blood, they all have their own linear absorption coefficient. Right, and then x is the distance traveled through that medium or of thickness. Obtaining diagnostic information using ultrasound. Right. So why are pulses necessary? So this is one of the most common questions that Cambridge is posted in its past paper questions in earlier years. So why are pulses necessary? So pulses are necessary to accommodate for both transmission of ultrasound and detection. So what happens is we send a pulse in the body. Right? It gets reflected when it gets to a boundary. Some of it gets reflected back. Right? So if we continuously send ultrasound, we're not going to be able to detect it because it will interfere with the incoming. The oncoming, the incident, and the reflected, they will collide. So the way it is done is we send our pulses, and then after detection, we send another one. That's how it works. That's how the sonogram works. So here's another important aspect of why pulses are necessary. So the time between transmission of a pulse and its received back, right? It gives the information as to the distance of the boundary from the transducer, and then the intensity of the received pulse gives information as to the nature of the boundary. It's like, what type is it? Is it a muscle bone boundary? Is it a tissue bone boundary? Is it whatever boundary it is? That is what the intensity of the received pulse gives. Working principles of ultrasound scanning. Right? So we have a question. This is a question that is usually asked. This one you can just memorize the facts if it ever comes back. These are the answers that you need to put in those lines that you get, the answer space that you get. So the question is, explain main principles behind the use of ultrasound to obtain diagnostic information about internal body structures. So they're saying, how does it work? How does the ultrasound work? So the answer you'd write is, first of all, a pulse is emitted by the piezoelectric crystal, right? And then the pulse is reflected at boundaries. It comes back. We detect the reflected pulse, and then the signal is processed and displayed on the screen. Right? Intensity of reflection gives information about the nature of the boundary, and then time between transmission and receipt gives information about the depth of the boundary. We just discussed that in the previous slide. Then we have, these are the terms that you may need to know. Impedance matching. When two media have a similar acoustic impedance resulting in little to no reflection. That's supposed to say little to no reflection. Right. So remember, our alpha was the difference between Z1 and Z2, and then Z1 and Z2 squared, like that. So if the Z1 and Z2 have a small difference, this will approximately be equal to 0, which means most of the incident ultrasound wave will actually be absorbed. And then we have something that is called a coupling medium. Remember, this is because of our acoustic impedances. So what you find out is that the greater the difference between the Z values, right, the greater our intensity reflection coefficient will be, meaning that lead to no wave will be incident, will actually be transmitted through the medium or will actually enter the body. So to avoid this, we have what they call a coupling medium, which is used to prevent this. I'll show you in the next picture. I'll show you what it is. So in real life, for when they diagnose women who are pregnant and they want to monitor how the baby is growing, how the fetus is growing, and all that. So they use a coupling medium and then they smudge it over the area they want to expose to ultrasound. We have attenuation of ultrasound, exponential decrease in power, intensity, energy of a wave as it travels through a medium due to absorption. Right. This is the definition of what attenuation of ultrasound is. It's just a decrease, exponential decrease in power or intensity or energy of a wave if it travels through the medium due to absorption. You may need this definition, so you might want to keep it in mind or write it down. Then we have the contrast media, a material that is used to reveal the outlines or edges of soft tissue in an X-ray image. Right. So this is when you want to. This we'll use it later. We'll look at it later when we want to when we're doing X-rays. That's when it's most applicable. Right. So that's a coupling medium in use. So I don't know if you can see, but we have shine that has been smudged over the belly. Right. That's the coupling medium. Right. It helps you the gel and the tissue have a specific acoustic impedance that is similar for the gel that is smashed on in the tissue. It's approximately the same. So Z gel minus Z tissue will be approximately equal to 0. Therefore, alpha, the intensity reflection coefficient, will approximately be equal to 0. And then all of the incident beam will be transmitted. If we don't use the gel, the specific acoustic impedance between of A and the tissue and Z tissue, right? It is very large. So literally none of the incident beam will actually be transmitted through the body. Okay. And then we have Partis X-rays.